Welcome to Academic Daddy's class. Today we're going to be doing derivation of the moment of inertia of a sphere. Before we start, let's get our tools ready. So tools needed. Remember, today I will be teaching you a super easy trick, something you've never seen before. Not like all those long videos they make on YouTube confusing you. Here, come closer. So the first thing I want you to notice is that if I have a circle, circle's area, when I change the area of a circle, I will get the circumference. When I say change, I mean when I derive this. For example, if I have pi r square, if I take the derivative of pi r square, 2 come here, you get 2 pi r. 2 minus 1, 2 pi r. Now, that means that, for example, something like a cylinder, which I know that has area, and that is what will be changing if I'm rotating it. The length remains constant, length, or you call it height, then the area. So which means that something like a cylinder which has volume of pi r square h, I'll use length. So which means that this part is the area and this part is the length. So what it means is that when I change the area of the volume of a cylinder, I'm going to get 2 pi r l. And this will help us when we start doing moment of inertia of a cylinder. Now for a sphere, which is what we are treating today, the volume of a sphere is given by 4/3 pi r cube, which means that if I change this volume, the way I change this one, I should have, come here, 3 times 4, 12/4, then pi r, 3 minus 1, 2, come here, 1. Yes, sorry, there's 3 under, not 4. So 3 here, 1, come here, 4. So I'm getting 4 pi r square. So why did I do this? Because what I will be using now is simply, another tool I need is my density. And when I talk about density, I know that density is equals to rho, that is RHO, is equals to mass over volume. Now, M here should be equals to density and volume, but we don't use M when we are doing inertia. What we do is change in M, differential mass. So that means that this will be equals to P, then change in volume. Density is constant, rho is constant, change in volume. And notice that when I change my volume, what I get is 4 pi r square. That is area. So when I change this volume here, what I got is area. So this is what I'll be using for my moment of inertia of a sphere. So it's going to be P, then 4 pi r square. So the M. So I'll replace it. So what it means is that I'll replace it. So that's why I listed out my tools. Now, another thing you need to note is that density, naturally, from here now, P is equals to density is equals to mass over volume. And which means that the volume is supposed to be mass over 4/3 pi r cube. But I'm not going to be using this 3. Reason, I'm sharing this 3 to X, Y, and Z. Let them take it. So I'm having just P equals to mass over 4 pi r cube. This is what I use for my density. Then this is what I use for my dm. Note it. Then you need to know that for a sphere, you know that what we are dealing with is a sphere. That's why we're using this. Now you need to know that for a sphere, the integral, the boundary for the integral will go from minus r to r. Notice that if this is a sphere, if this is this way and is moving, it's not covering like totally, should I say, the way you have it for a circle. It's not really that, should I say, radius being the same all through. So I have minus r to r. So with this said, let me come and substitute. So I see this for my density, I see this for my dm. Then remember that inertia, moment of inertia is equals to integral of r square dm. This is why I put all those our 2's out, equals to. So dm now, replace the m with p, density 4 pi r square. So I'll have integral of r square density 4 pi r square. Then I will now say for the inertia, I will now have integral of, okay, let me write out all these things one side. So I will now have p 4 pi, then integral of r square 4, pi, what am I doing? So I will now have inertia, to be equals to p 4 pi, pulling all those things out, then integral from negative r to r, then I have r square, which is 4. Now, if I know this, what am I differentiating with respect to? Notice that when I did this volume, what I actually changed when I did this was the r square. That is what I differentiated. So I'll say with respect to r. If I want, I'll put it. If I don't want, I will not put it. Why I'm putting it is so that you don't get confused. So the r. So by the time you integrate this now, you have add 1 here, divide by that power. So you have r raised to power 5 all over 5 from negative r to r. So this is p 4 pi. So I can choose to say integral, the inertia is equals to, so inertia is equals to p 4 pi, let this come over here, is the same thing, all over 5. So r raised to power 5 minus r raised to power 5. This changes to plus, minus. So I have 2 r raised to power 5. So I now have p 4 pi. So the next thing is to remember that my density is equals to something. When we started, we made density, we gave density to be m over 4 pi r cube. Remember, we shared the 3 down to x, y, z. I don't need it. This is my easiest trick to getting this, and it's always steady. If you like, don't believe it. This is genius. Alright, now I'll have m over 4 pi r cube, then have my 4 pi, then have my 2r5, 4 cancel 4, pi cancel pi, r5 cancel r here, 3r here, you have 2. So when you put it together, you simply, okay, then remember that when we did this, everything here is being divided by 5. Everything here, remember that this is for density here. Look at it. So everything will put that here. So this is supposed to be having over 5. So let me take that over 5 to this side. So all over 5. Yes, now it's been divided by 5 before I did this. And if it's here, even if I move it to here, because they are being separated by multiplication, so I'm now having moment of inertia of a sphere to be equals to 2. Then I have my m, I have my r raised to power 2, I have 5. I can put this 5 here. This is the moment of inertia of a sphere. Very simple, very easy. Thank you. Subscribe, share. Now for that of a cylinder, let's use the same approach. Let's try to use the same approach. So let's say derivation of the moment of inertia of a sphere. So we'll come here. We'll now say for a cylinder, or a disc, is the same thing. Well, remember we said that for a disc or a cylinder, that it is given by pi r square L. That is area is given by area. Everything here is the area of a circle. Everything here is the length. So what will change? So we now say, if we consider the density of a cylinder, is going to be mass over volume, and that this is going to be mass over area and length, rho. So if I make m such a formula, it will be equals to density A L. But remember we said that the differential mass, the mass that is changing, that is going to be, you always get the mass that is changing, because that's what inertia is, when mass is changing, rotating. So you now see that what will change is not the length. Remember we drew this, length will be steady. Is this volume, this area, that will be rotating, that will be changing. And what makes up the volume is area and length. The area will be changing. So we now bring out P, bring out A, L. Then area here, when you change this area, so the A, and when A first of all is pi r square. From what we analyzed here, A is pi r square. Then when A change, when you change this A, when you derive pi r square, you now see that it will now be 2 pi r. That is derivation carrying these two to multiply this, then minusing 1. So you have 2 pi r as the changing a. So then put my PL. So this is my dm. So let's now carry it to integration. So to moment of inertia. So derivation of moments of inertia of a disc or cylindrical rod. That's what we are doing. So you now see that moment of inertia is equals to integral of r squared dm. So inertia will be equals to integral of r squared. The m is going to be PL 2 pi r. Now it is the r that is in a that we use to derive this. So I can say the r. If you don't want, you don't put it. I just put it so that you don't get confused when you see it in textbook. It makes no use, but it's just telling us that this is what we are deriving in respect to. So inertia will be equals to, pull out everything you have one side, so that I have PL 2 pi integral. And for a cylinder, notice that this is a circle, is steady, everything is the same. So the boundary always go from 0 to r. You need to know this. The boundary always go from 0 to r. While for a sphere, it always go from minus r to r. So very important. So I'll just put r and 0. Then r square here. Then I have 1r here. So r times I becomes r cubed. So when I do this now, taking the integral, I'll now have add 1 to the power, divide by the new power. So I'll have r raised to power 4 over 4, boundary of 0 to r. So I now have PL 2 pi equals to the inertia. So now notice the moment of inertia will be equals to anything times 0 divided by 0 is no use. So I'm just checking when r is there. So I'll just have my P for this density. Density is going to be, remember, so density, remember from here we did density of a sphere. So density of a sphere is equals to m over area is pi r square. Then you have the length. So carry it and put, so that I have m over pi r square l, then times 2 pi, then times r raised to power 4 over 4. So when you do this, pi cancel pi, r square cancel 2 here, you meant 2 1 2 here 2. Then yes, sorry, remember, yes, remember that this density, this is density here, is carrying an L. This is density, everything here is for density. So there was an L, multiplying it, which is this PL. So L cancel L. So we've succeeded in cancelling everything that is supposed to be cancelled. So moment of inertia is going to be just bring out my m, bring out my r, bring out my square, then I have 2 here down. So moment of inertia is equals to 1 over 2 mr square. Believe it. So there you have it. Thank you. Subscribe, share.